Hi, in this video we're going to be talking about the second part of 14.2, which is how to prove a limit exists if you think it does, or if you're told to show the limit exists, all right? Now, in the last video we talked about all the different things you would do to try to avoid this, because this is kind of annoying, especially if you have to get the hang of this with a number theory. If that scares you, it's really not that bad, but it does take some getting used to. So I guess the general advice I want to give you is that instead of checking all the possible paths, which is impossible, right? We can't check every path individually. We can check a lot of paths at once, but there'll always be functions we didn't check. So there's more formal proofs that you can see in the book, but in this video I'm mostly going to focus on, we're going to try to use inequalities to squeeze the limit. Now, squeeze is actually a technical term here. For once, that's not a joke. Remember the squeeze theorem. Okay, if you have an inequality where f of x is less than or equal to g of x is less than or equal to h of x, and the limit as x approaches a of f equals the limit as x approaches a of h, and they both equal the same number, then the limit as x approaches a of g of x is also that limit. Whenever I teach this, I usually say the picture is worth 1,000 words here. Okay, if to h of x in red, h of x is some top function, and f of x is some lower function. They happen to have the same limit at some value a, and f of x is always bottom, and h of x is always on top, and then g of x is always in between them. Then as g of x approaches that place where they both have the same limit, where else can g go? There's nowhere else for g to go besides to get squeezed by those two functions. The same thing is true in Calc 3D land for surfaces, right? If I have one surface that's always above another, then they are going to squeeze this other surface between them. Unfortunately, I can't draw that visual field too much, but you can picture that, right? Because in 3D space, we can literally picture you're squeezing like Play-Doh between your two hands. The Play-Doh is going to end up in the location where your hands are meeting. Those are two 3D surfaces squeezing together. They will force a third surface to have the same limit at that point, right? That's literally what we're saying here. We're also going to use one more fact, okay? This is the idea that if the limit as x approaches 0 of the absolute value of f of x equals 0, then the limit as x approaches 0 of f of x was 0. This is a consequence of the fact that the absolute value only is ever equal to 0 when the inside is equal to 0, that the absolute value is a continuous function, and that in some sense, by flipping all the negative numbers to be positive, I've made things less likely to converge. You might remember this from Calc 2, talking about absolute convergence versus conditional convergence, but that's kind of an obscure topic. So in general, I'm just saying that, well, I've made everything that was negative positive now. If that stuff all goes to zero, right, as I approach zero, if that stuff's all going to zero, then it must be true that we're still going to go to zero, even if I take off that restriction that everything had to be positive, that all my numbers were positive. Okay. This is very hand wavy, but we are going to use this fact a lot. So in 3D terms, if we have a limit as x comma y approaches 0 comma 0, and that was 0, then this limit is also going to be 0. I'll say it again, y. There's a bunch of hand wavy explanations. There's formal proofs of this fact, okay? Like everything else I talk about in these videos, there's formal proofs of this fact. The main reason is because the absolute value function is only ever going to be 0 when its inside is equal to 0. And because of the continuity of the absolute value function, doing the limit of an absolute value is the same as doing the absolute value of the entire limit. Okay, that does not work in general. I don't want to see you using that too much, but that is true. If that whole thing equals 0, then it must be true that the limit inside had to be 0, right? There's no other way to have an absolute value equal 0 except for its contents, its argument, its inside to be 0. Okay. With that piece of technology, it's going to make a lot of stuff we do a lot easier. So here, let's look at, I'll just tell you. We'll say prove this limit as x comma y approach 0, 0 of 5x squared y over x squared plus y squared equals 0. Now, if they didn't tell you to prove it, what would you do? You would check all of the paths. You would check x equals 0. You check y equals mx. You'd look at their common ratio, and I'll point out that the common ratio doesn't exist. The top it's 2 to 1. The bottom it's 2 to 2. Okay, that's a sign that things aren't working out, or things are going to work out to make the limit exist. But again, that's not enough to check or show that all the paths go to 0. To show all the paths are going to go to 0, we're going to use the squeeze theorem. And in order to use the squeeze theorem effectively, we're going to start by taking the absolute value of the entire limit. There's a bunch of reasons for this. Again, one of the reasons is so we can use that fact that we just pointed out in the last page. One of the reasons so that automatically this is greater than or equal to 0. Right? I hope we see that. It's an absolute value. It's got to be greater than or equal to 0. Now, inside this absolute value, 5 is always positive. X squared is always positive. X squared plus y squared is always positive. So that absolute value is not doing anything to all of those. So I hope you agree with me when I say we really are talking about this situation. Okay. Now comes the trick. And I call it a trick because to some students, what I look like I'm about to do is gibberish. I'm looking at x squared over x squared plus y squared. And I'm going to notice that x squared over x squared plus y squared is always less than or equal to 1. So this whole thing is less than or equal to 5 times the absolute value of y. This is the real key step. I'm going to put a star next to it, but I want to justify why the heck I was able to make that. This is what I would call using a math fact in some situations, but math facts seem arbitrary. It is a fact that that's true. You might not have ever heard that before. Let's start from building blocks. All right, start from something you know for a fact. Do you know for a fact that 5x squared over x squared is equal to 5? Notice how I'm taking something from the top, I'm taking something from the bottom. I really want to just have the absolute value of y. That's what you're focused on. All right, I took the top, I took the bottom. 5x squared equals 5. No argument, right? Therefore, if I add a tiny positive number to the bottom, right, and y squared is a tiny positive number, what happened? Did it get bigger than 5? Did it stay the same as 5? What happened? You would agree that, like, if y was any number, really, it would be less than 5. But because y could have been 0 still, we have to say it could be equal. And this is because y squared is always positive, or 0. Does that make sense? And that's really all I did. I took this junk and I replaced it with somebody who is always going to be less than or equal to. You could go a step further and multiply by a positive number, absolute value y, and get exactly what we talked about. But it's not really how I think about it. But if that helps you, if it helps you to build your inequality from scratch, please do that. It really will help you to not lie. And I said this in the last video, that's the hardest part. You're the easiest person to fool, it turns out, when you're trying to prove things like this. You're going to make us jump in logic, and you're not going to understand why you're making that jump. You're just trying to get the problem over with. You're tired. You don't want to do this anymore. And I'm going to catch it. I'm going to see it's wrong, mark you wrong. That's going to be it. Okay. So, hopefully we've justified that this is true. Okay. All right. So, since 0 is less than 2 or equal to our big giant expression is less than or equal to 5 absolute value of y, and we're going to do a limit as x comma y goes to 0, 0 of 0, and we're going to do the limit as x comma y goes to 0, 0 of 5 absolute value of y. Where did I get these two? I'm doing a limit of the guy on the right, limit of the guy on the left and the limit of the guy on the right, like the squeeze theorem says. The limit of the guy on the left, limit of the guy on the right. Where's this limit going? 0. Where's this limit going? 0. Therefore, the limit as x comma y goes to 0, 0 of this whole thing equals 0. Therefore, our limit up top, and I'll just write it again for good measure, copy and paste, equals 0. Okay, and again, seems like cheating. We kind of are. It's kind of unjustified to use something we're not proving, but this is not a math reasoning class. We're not just trying to prove things. If you continue in your math education, you'll see why, again, on that last page, the theorem's true, and more formally, but this will work for us. This will actually get you through a lot of the proofs that maybe people in your shoes previous years had a hard time with. I want to do one more example of a proof like this. And then we're going to switch to talking about continuity, everyone's favorite topic. I mean, it's just much easier. We're just going to talk about where is the function continuous. All right. Okay, let's do x to the 8th, y to the 4th, all over the 4th root of x to the 16th plus y to the 16th. Wow, is that ugly, you might say. I don't even know where to start, you might say. Okay, well, again, what do we always do first with limits? Where's the top going? Where's the bottom going? What a surprise. Quelle surprise. Que sorpresa. We're not that interested in it anymore, I'm sure. Does that mean DNE? No. Does that mean 0? No. You could check other paths. I assure you they're all going to work out to be 0. Why? Because I'm going to prove to you that this limit is going to 0. What's the first step? Take the absolute value, you might say. But in this case, you might notice, this is one of the reasons that absolute value theorem works. The absolute value is not doing anything because every single guy in here is positive. So we're much more interested in how to eliminate the problem. Now, what do I mean by the problem? Okay, we're going to try to look at what's going to cancel out naturally in an inequality, all right? And the key is to look at the powers as usual. Okay, on the top, things are pretty transparent. We have an x to the 8th, we have a y to the 4th. What are the powers doing on the bottom? What's the degree on the bottom? Now, you might say it's to the 16th power, but that's ignoring the group's radical. So if it's 16, and then what's the 4th root is 1/4, overall, the bottom is a 4th power. And that's why I'm going to use the fact to combine these guys. Really, we're talking about a 4th on the bottom and a 4th on the top. Okay. Bear with me here. Here's my proof. I'm going to do y to the 4th over y to the 4th is 1. No big surprises there. That means y to the 4th over the 4th root of y to the 16th is also 1. I just literally rewrote the bottom into this really complicated expression. Why? Because I'm going to try to get this back. So now you might see how this is going to go. Oh, if I add something small, if I add something positive in the denominator, under the square root, what effect does it have on this inequality? This equality will turn into an inequality. That's what we're doing. And so if I multiply both sides by the positive value of x to the 8th, you'll see that this whole thing is less than or equal to x to the 8th. Because this whole thing is less than or equal to 1. Okay? That's the trick. So sentence time. Since 0, right, we agree that this guy's already always positive, or 0. Less than or equal to x to the 8th. We prove that. The limit as x comma y approaches 0, 0 for x to the 8th is 0. And the limit as x comma y approaches 0, 0 of 0 equals 0, we know that the inside, the middle guy, Goldilocks, baby bear, whatever, also must be going to 0. That's it. I hope this doesn't seem that bad. The hardest part is the quote-unquote creativity it takes to see how to make those inequalities happen. But once you get the hang of it, it's pretty straightforward. I really think you guys will get this. And if not, please come to office hours. And I'm happy to help walk you through some more examples. Okay. So we're going to end with a brief discussion of continuity. Mostly this is just retreading what you would assume to be true after calculus 1. Okay? So continuity. A function is continuous at any point on its natural domain where it's defined. It's a different it's. Okay, that's all I mean by natural domain. Okay, you'll see this when we do some examples, but really quick, establishing some ground rules. Polynomials are continuous everywhere. Rationals, so that's a polynomial divided by a polynomial, are continuous. Rationals are continuous everywhere except denominator cannot be 0, because that would be outside of this function's domain, right? I hope that makes sense. And just a third ground rule, compositions of continuous functions are continuous. It just means if we're just mixing together continuous functions, we don't have to worry about new issues arising. If you add two continuous functions, they're still continuous. If you multiply continuous functions, they're still continuous. Exponentiate, blah, 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 blah. Okay, so it lets us do all our math. So, quick examples. Here's a surface, here's a function. X cubed plus xy plus y cubed over x squared plus y squared. Okay, where is that going to be continuous? It's continuous on the set, remember it as a set, all of the xy pairs such that x squared plus y squared is not equal to 0. Now, if you're astute, there's only one way for x squared plus y squared to be equal to 0. And that's if x equals x comma y, not both 0. Okay, that's another way to write that same idea. If they're both 0, that's the only way the denominator is going to be 0. Writing it this way is fine. It's also true. But you should start to understand that the only way x squared plus y squared is going to be 0 if they both are 0. What happens if we were going to 0, 0? We would see if the limit exists. You can do everything we were just doing in the last, 2 videos, including this one. Let's do a couple more just to get a feel for this. If we have f of xy is the square root of x times e to the x over y, what a cool function, all right? What are the restrictions? E is fine by itself. Exponentiation is fine by itself. But its exponent is not so fine, because the exponent's a fraction, the exponent's a rational. So we can't have y equal to 0. What about the square root? The square root's fine everywhere besides x being less than 0. So we're saying x has to be greater than or equal to 0. And how do we write that in set builder notation? This notation, such that, same thing, x greater than 0 and y is not equal to 0. That's all it takes. You don't want to mix things up. You want to make sure you're saying and, not or. Don't try to use funny notation. Okay? We need both these things to be true, or else this function is not defined. It's basically the same exact thing as finding a function's domain. If you're wondering what that looks like, there's a whole space of 3D space where x is larger than 0. We're talking about like the positive part of the x-axis, okay, and all the space above and below it and next to it. And y not equal to 0 just means we can't be on that xz plane. That's what y equals 0 would look like. One more. Ooh, three letters. We didn't do limits with 3 letters. It gets even more complicated, and we don't want no part of that in some way. It's similar but different. Luckily, I guess I'll say this about limits really quick. It doesn't get any worse. You can't go any worse than having infinitely many paths. What do you start to do? You start to use parameterizations. You start to use vector curves to approach points. And then you have to get really creative with how you're going to approach things. And that, I mean, the book's clearly not that interested in it. If you look at the section it has on limits with 3D functions, it's not that bad. It's not that in depth. It's just to say that, hey, this keeps getting worse. But luckily, we mostly want to talk about continuous functions, just so we don't have to worry about the headaches that discontinuous functions have for us. So here we go. We don't want the bottom to equal 0. Whoops, z squared minus 4 cannot be 0. So we can have this equal to 4. What would that look like? This would be the sphere with radius 2 centered at the origin. So we're saying it's all of 3D space, right? It's all of 3D space, just not that ball. Because again, a sphere is just, sorry, not ball, sphere. Just that surface, the orb that would contain the ball, okay? It's just the surface, it's not the inside. We could go inside the sphere, we can go outside the sphere, we just can't be on that surface of the I don't know, sphere. I don't want to say ball, because ball can mean the inside of the ball. So I didn't write out Kant on above. Now we're going to say the 3D coordinate, such that, again, it's not very creative. We're just putting that condition inside. That's it. So I would focus on the proofs more than continuity. I'm pretty sure this continuity stuff is pretty straightforward. See me in office hours if it does make sense. And thank you for watching. Thanks for your attention.